a quick overview of the main topics in precalculus. What is precalculus? Now, at the very end, I kind of say what the purpose of precalculus is. It's a transition to calculus. The idea is to make calculus as easy as possible, to make it accessible and as easy as possible. Topics in precalculus, and forgive the use of color here, but most headings are in white and details in other colors. Okay, so analytic geometry in the plane. With analytic geometry in the plane, we kind of start off with the Pythagorean theorem, the calculation of the distance between 2 points in the plane, the idea of midpoint. This is all rudimentary. Also, I could include here circles. I didn't write it down, so I'm not going to try to squeeze it in. But all that is elementary. Now, when we go beyond these elementary ideas, we go to the idea of conic sections, parametric equations, and polar coordinates, all of which need to be included in a complete precalculus course, but many of which end up being either glossed over or omitted, and this is much to the detriment of any student who's going to go further in mathematics. These ideas are essential. You don't want to be tripping over them when you're trying to learn more advanced mathematics. In any case, analytic geometry in the plane. Properties of functions. Linear functions, power functions, quadratic functions, exponential functions, and trigonometric functions are quite fundamental. Now, we can combine these functions in various ways. Actually, quadratic functions are not quite as fundamental because a quadratic function really is nothing but a second degree polynomial, but they're so important that I give them an extra classification. But linear, power, exponential, and trigonometric functions are the basic functions that we use in most undergraduate mathematics. We invent other functions, we combine these functions to form other functions. We take inverses of exponential functions to get logarithmic functions, inverses of trigonometric functions to get the inverse trigonometric functions. We combine power functions to get polynomial functions. Counting number or whole number power functions can be added to give polynomial functions. We divide polynomial functions and we get rational functions, a polynomial divided by a polynomial, and so forth. And these are the elementary functions, the basic functions of at least undergraduate level mathematics. And as we say here, we say we can form sum, products, quotients, composites of these functions and build up quite complex functions, and we can use these functions to model a broad spectrum of real-world phenomena as well as theoretical ideas. We need to be able to construct graphs of these functions. Unfortunately, students think that graphs are constructed by punching them into a calculator due to the extensive and criminal misuse of calculators at this level. And excuse the editorial comment, I think the vast majority of mathematics faculty pretty much agree with what I said there, though. Rates of change. Rates of change are extremely important and reasonably easy to understand in the context of precalculus and in the context of these basic functions, so that we can move on to the study of calculus, in which rates of change are completely fundamental. And then the whole idea of functions and function families as entities, as mathematical entities. Students come into precalculus hopefully knowing how to do algebraic manipulations and a few other things, and hopefully they can be pretty good at those things, but they haven't begun to abstract things to the point of understanding functions and function families as entities. I'm not going to detail exactly what I mean by that. I'll just note that a typical student coming out of precalculus still really has no clear picture that there are such things as linear power, polynomial, rational, exponential, logarithmic functions, and so forth. Doesn't understand the classification. And it's extremely important to understand this classification. It makes calculus much easier if we understand these classifications so that we can then apply calculus to these classes of functions, to these families of functions, to these entities. Okay, triangle trigonometry is typically taught in a precalculus course, and triangle trigonometry is extremely powerful, extremely useful. I don't think I need to explain why. Very, very important topic. Trigonometric identities, another important topic, leading to a lot of topics, a lot of ideas that are developed in higher mathematics. And when I talk about higher mathematics, I'm really talking beyond calculus. A lot of the things that we deal with there have roots or profound applications or come from things like trigonometric identities and similar ideas. Okay, we have vectors. Vectors is another absolutely essential tool for application of mathematics at the lower undergraduate level and moving on to the higher undergraduate level and beyond. So we want to cover vectors through dot products and projections. Now, if we got the trigonometry, this is not particularly difficult to accomplish. So we want to get at least this much of the idea of vectors so that we can apply vectors in physics, engineering courses, so that we can use vectors in first year and second year calculus and do so fluently. Matrices are quite important. Not so much for calculus. So in a pre-calculus course, matrices are important, but not so important as a foundation for calculus. They're very important as a foundation for linear algebra and the things, the topics that grow out of a study of linear algebra. So linear algebra is, in a sense, as fundamental to lower level undergraduate mathematics as a building block for higher level undergraduate mathematics as calculus. So we do include matrices in this transition course. So maybe I should have listed here transition to calculus and linear algebra. Okay, and under matrices, matrices arise naturally when we try to formalize the process of solving a system of simultaneous equations by elimination. And that leads us to a very simply, an easily understood process called row reduction of a matrix. And then we're led to the idea of an identity matrix, inverse matrix, determinants, Cramer's rule. All of these things then can be applied to systems of equations, but they also have applications far beyond that. Okay, sequences and series, another very important topic. This comes up, should come up in a second semester calculus course, or at least no later than a second semester calculus course, to help formalize the ideas of the calculus and how it can be applied in subsequent study of mathematics. Okay, so sequences and series, and right in a pre-calculus course we want to look at patterns of sequences and series, classification, notation of sequences and series, summation, the idea of summation of a sequence, and then we have applications in modeling. And something that I neglected to write down and had to put in the middle here also, we need to be able to put expressions and equations into useful form. And we do this by more deeply understanding algebra as a system and putting it to practice in putting expressions and equations into the forms in which we can apply them. And also solving equations. We solve equations. We can solve, of course, we come into precalculus being able to solve a linear or quadratic or power function type equation, but without much experience or, typically without any experience in solving exponential, logarithmic, or trigonometric equations. We learn to solve equations of all types and reinforce the algebra that's required to do so. So, and again, I think I said it, we have applications in modeling, the ways in which the mathematics is used. So there's kind of a picture of what we need to cover in a precalculus course. And I'll comment that very seldom in a precalculus course does everything get covered in any kind of a deep fashion. But having covered it here, it makes everything easier in the future. So precalculus can be a really pivotal course for any student.